Hi everyone. This video is the solution to example 3 on the topic of unit load method. In this case, we have a non-uniform section. So these first 3 meters have a second moment of area, which is 2 times the second moment of area in this last 2 meters. And in this problem, we're going to learn how we deal with this type of problems. Again, we're talking about unit load method, and we're talking about finding the vertical deflection at the free end. So if we want to find this delta, by now, you should know that we're going to split this into real structure and virtual structure. And the real is nothing more than the load that is original, and the virtual is the load of 1 in the direction of the displacement that we want to find out. So if we want to find that vertical delta, we need a vertical 1 in the same place. And then for the real one is nothing more than the 48 kilonewtons. So it looks like this. Bending moment diagrams couldn't be simpler. So in this case, they're both triangles. So the 48 is going to look like this, and the 1 is also going to look like that. We need to check the span of the cantilever. So it's 5 meters and 5 meters, which means this moment here is going to be 5, and then the moment here is going to be 48 times 5, which is 240. What is tricky about this problem is that the beam has different second moment of areas in different regions. So we need to split this diagram here at the 3 meter mark. So this is going to be 3 meters, this is going to be 2 meters, and we need to split it like that, and that will change our calculation. So one of the first things we need to do is to find these moments here in the place that we're splitting it. In the case of the 1 kilonewton, the bending moment will be just 2, and in the case of the 48, the bending moment will be 96. So now, when we try to find the equation for delta, and again, let's write down the generic equation, which is the integral of this bending moment diagram real times the bending moment diagram virtual, all of this divided by EI. The fact that our EI is not constant means we need to split this integral into 2 different regions. So at the end of the day, what this means practically is that we need to do a trapezoid times a trapezoid, which is going to be this trapezoid times that trapezoid. All of this divided by the EI of that bit, so in this case is 2 EI, so the beam is a little bit stronger, 2 times stronger in this case, plus, and then there's going to be a triangle times a triangle divided by the EI of the beam. And this is it. So now we go and get our table, and we need to start using it to calculate this delta. So delta is going to be trapezoid times trapezoid. So we have this here, that will be trapezoid times trapezoid. So I'm just going to write that down. So 1 over 2EI first, and then I'm going to write all of this down. So 1 over 6, then I need a big square bracket, then 2C plus D times A plus C plus 2D times B, and all of these times L. And then I close that bracket, plus, and now 1 over EI, that's the 2 triangles. So 2 triangles growing in the same direction will be this, 1 over 3 ACL. And this is it. So it's going to be quite tricky to do this trapezoids, but the problem is not difficult to set up. So at the end, we get 1 over 2 EI. And now we need to figure out what is this C and D and A and B. So if we look at the 2 trapezoids, they're growing in the same direction. So C is on the left side and D is on the right. A is on the left and B is on the right. But on this, in our case, since our trapezoids are growing in the opposite direction, right? These trapezoids here and here are growing from the right to the left. We need to swap this definition. So C is going to be the smaller one. So I'm going to set up C to be 96. So this is going to be 1 over 6. And now 2 times 96 plus 144 plus 240. And now I'm going to multiply this by A. And A should be the smaller value of the second triangle. So it should be 2. And now I'm going to add 96 plus 2 times 240 times, and now the other one should be 5. We close the big bracket, and then we multiply this by the length of the trapezoid. So this length here is not going to be 5, but it's going to be 3, because it's the length of these trapezoids, okay? That's these 3, or if you want, these 3. And this is it. Took a little bit of work, but this should be correct. And now we add the triangle, so we add 1 over EI, And the triangle should be easier. So 1 over 3 times 96 times 2 times 2. Let's have a look. So 96 is the value on the first triangle. So let's patch it here in green. So 96 is that value. 2 is the other value, and then 2 is the span. So this looks okay. At the end, this is going to give me a number that should be divided by EI. And I just need to go to the calculator to find it out. So I'm splitting this calculation. So this is 936 from the first part, and the second part will be 128 divided by EI. So note that the 936 is already divided by 2 because of this 1 over 2 EI. So at the end, this is equal to 1064 divided by EI. And again, the fact that it's positive means my displacement is down, which was what I assumed at the beginning. One interesting thing about this problem, we can look at this 936 as the part of this 1064 that is created in the first 3 meters. So even though the first 3 meters are 2 times stronger than the last 2, because the bending moments are a lot larger in that region, at the end, that region is still much more responsible for the displacement than the second region. So to explain this again, this is the first 3 meters, and this is the last 2 meters. Even though this green part is 2 times stronger, it's still responsible for the vast majority of the deflection. Okay, so it's good that you guys notice that. So thank you for watching, and have a nice day.